in the hearing lab, one of the things that we're going to be looking at is sound localization. It's like, how do you know where the sound is coming from? You have your eyes shut and somebody snaps or somebody walks, you kind of usually know, are they coming from my left side or from my right side? How can we do that? What's the information? What are the cues that our nervous system has that allow us to know where the sound is coming from?
How loud the volume is?
Okay, so one thing is volume. What else? There's got to be another piece in this. So it can be about volume or intensity. And then what else what about the volume and intensity?
Does it have to do with directionality of the bending?
No. We're kind of bigger picture here right now.
Is it just what ear is receiving?
Yeah, so you've got two ears. So if there is some sound that's happening over here, and where is this dog barking or something? This sound is going to be louder in the closer ear than in the farther ear. That's one of the cues that we can use to know where it's from. We call it interaural intensity differences. How loud is the sound in one ear versus the other? That's information your brain can use to figure out where on the clock is this thing. What's another clue or cue that your nervous system can use to determine where in space this dog is barking? So sound, has anybody ever been in a thunderstorm? Like, what do you notice about like thunder versus lightning?
You can see lightning, you can't see thunder.
Okay, yeah, but
Matt,
The
What's
thunder.
You see the lightning before you hear the thunder.
yeah, you see
Depending
the
on how
lightning.
far away it is how
Yeah.
long it'll take for you to hear it.
Sound moves pretty slow. Sound moves around like 300 meters per second. It's pretty darn pokey. That's why you see like the flash, because light travels really fast. Gets to your eyes almost instantly, but the sound is like doop de doop de doop, and a few seconds later, the sound finally gets to you, and you're even if you've just been watching somebody chop wood across a lake, it's just like it's just weird. So sound is slow enough that your nervous system can actually detect the difference if the sound's hitting one ear versus the other ear first. We call it interaural timing differences. If something is on one side versus the other side, it's going to hit that ear on that side before it gets to the other side. And that's information your brain can use to figure out where is this thing coming from. Right? I mean, this is one of the ways when I was talking about knowing it, kind of making sure you don't get caught by the tiger. Your brain can use these interaural intensity and timing differences, especially the timing differences, to kind of just sample what's happening in different sections of space around you. and kind of just hone in and kind of not worry about the other stuff as much. So given this, we are actually going to do a experiment that you're going to have to do at home with a friend or loved one, or where you basically make a noise. They have their eyes closed and you make a noise and they have to figure out where it's coming from. And you're going to check out, right and left and front and back and above. Where do you think is going to be the most difficult to localize sounds from?
Behind.
Behind
I would say
why?
above.
Or above why?
Our ears are pointed forward.
Um,
The equidistance.
yeah, the equidistance. If you think about using this timing or intensity difference, anything on the midline, it doesn't matter actually if it's above you or behind you or in front of you for that matter, it's a lot harder to make sense of it because you don't have this difference between the two ears. If it's equidistant between the two ears, both ears are experiencing the same thing. There are some subtle things that you can do, like in the shape of your ears does make a difference. Sound coming in from the front will get modified differently than coming from the back because your ears are not symmetrical. But that's way more subtle than this timing or intensity difference thing. So when you don't have any interoral differences, it can get really tricky trying to figure out what is going on. So you're going to do that. In fact, let me just get into that. We go back into our okay, I'm going to go previous. Let's go share screen. So here is special senses hearing, sound localization. Ask your partner to close both eyes, ring a bell. So instead of ringing a bell, just snap your fingers. You don't need a bell. You can just, hopefully, yeah, you know how to snap. If you don't know, this is a good time to learn to snap. Or you can do something else. It doesn't matter. It has to be a sound. And you're gonna test and you're gonna record. It's not just here, there. Make sure that you are kind of rigorous about this. Check in front of your subject, and they have their eyes closed. See where they point. Record. Did they get it or not? Check in back of your subject. Be careful about giving them more information than you mean to. Like if you're shuffling around, they can kind of figure out what you're doing. So make sure that you're kind of subtle and they don't know where the next sound's coming from. Maybe you walked over here, but now you put your hand over there or whatever. But it should really just be about localizing the sound and not being a clever detective trying to detect, like, where is this person walking around me or something. Check to the left side of your subject, to the right side of your subject, record that. Check above your subject's head. So for each of these, you're going to record your data in your lab book, and then again, can it be localized equally at all? Well, and how do you explain your observations? Again, just from our discussion, what are you likely to find when we do this?
But above and behind are harder to localize.
Yeah, that's what you'd expect and what you very likely will find. Some people are better than others at using the more subtle clues. Even the clothes you wear affects your ability to localize, and because it changes the nature of the sound landing on your ears. Like there's everything people have done stuff, just changing your clothes, putting on a coat or a jacket or a sweater changes the way that sound is reflected or absorbed off your body and the information that your ears are getting. And very quickly, your brain recalibrates to the new baseline of, okay, what are things, where are things, and what do they sound like? And let's recalibrate for this outfit and how to best interpret the sounds hitting my ears. It's kind of crazy. So that's part of the lab is you're going to do this. It's not going to take too long. It should be actually pretty fun. I find, yeah, I don't know if these are as fun at home as they are like when you do them in lab. In lab, it's definitely fun.
We need someone to assist us, right?
What do you mean?
Like we need someone at home to help us like do the snapping. Or we just do it on our own.
I don't know if I understand your question.
Yes, you'll need somebody else to do the snapping because if you're snapping, you know what area you're snapping.
Right.
It
So
takes two people.
it's two people, right? If you're snapping, then you have a subject you're snapping at, right? Or if you're the subject, then someone's got to be snapping at you. Does that make sense?
Yeah.
Yeah, no, so this has to be with somebody. So frequency range of hearing. All right, so this one, we are not going to do the part A, forget about part A, but part B we are going to do. And it's, normally we would do it in class together, but I'll show you in a few moments how we're going to do this. This has to do with how you lose your high frequency hearing as you get older. Those hair cells, that high frequency part of the cochlea start dying and they don't come back. So basically, let's go into the next. So this is in the doing the hearing lab part module of the hearing lab, which is on in your Canvas right now. So sound localization, it says, do like in the lab manual, but instead of ringing a bell, snap your fingers. And again, there's a little video if you're not quite sure, you can follow this and it'll help you like think about it.
Here, or I guess I'm mirrored on this picture.
Right, so she's gonna, tell you, she'll tell you the stuff I was just telling you to give you more background as well. And for frequency range of hearing, A, ignore this part. For B, you want to see what is the highest frequency that you can hear. When you are young, you can hear up to like maybe 18,000 hertz, 18 kilohertz. As you get older and older and older, that highest frequency that you can hear becomes lower and lower and lower and lower. Both of these basically sweep a frequency from low to high, and you have to decide when you stop hearing it. So like, I really don't like the fact that it's saying how old are your ears, because it really depends on your experience and your genetics and stuff. But what I want you to look at is don't forget the how old is your ears. Think about what is the highest frequency I can hear. That's what's really important as you do these. And they're both pretty similar.
Hey, how's it going? This is Joe Myself.
So,
Today we're gonna try to find out how old your hearing is.
yeah, it's like, it's not how, it's like, we're going to find out what's the highest frequency you can perceive, and it's loosely correlated with age. That's what he should be saying.
I'm Joe, and I review speakers and audio equipment in all different price ranges here on YouTube. and I rely heavily on my ears. But one thing I do is I do a lot of measurements, and that's because I can't trust my ears 100%, and neither should you. The reason I say that is because as we age, our ability to hear high frequencies starts to decline. A test we're going to be doing today is to try to figure out how old your hearing is. If you're interested in knowing the formula that I use, I'll leave that in the link in the description. This is just for fun. It's not a medical test. So this is how the test works. I'm going to be running some frequency sweeps from high to low. And what you're going to try to find out is where you can start hearing the high frequencies. This does require for you to use headphones. It will not work if you're using your phone or a laptop. So also make sure not to turn it up too loud. If I sound reasonably loud right now, then keep it at this volume here. So when the test starts, it's going to start playing tones immediately. Notice when you can start hearing the sound.
Yeah. Right, so it's going to be going. So when you first hear it, you're going to start hearing this high-pitched tone. As soon as you actually start hearing the tone, don't worry about the age. What you care about is the frequency in hertz in the corner here. That's what I want you to pay attention to. And again, over Zoom, it doesn't work at all. The Zoom is totally messing with the sound. But if you're using like headphones or even good speakers on your computer, it should work fine. So this, you can use this one. You can double check. This other one is the same basic idea. Again, for whatever reason, people get off on this. How old are your ears?
As we grow older, we often lose the extreme ends of our hearing spectrum. So, okay, if you can hear 8,000 hertz, you're both alive and not hearing impaired. But let's keep raising the frequency.
Right, so this is going the other way now. You know, right, so like for me, literally when people are playing 15,000 hertz, like when we do this in the classroom, it's actually changed over the years since I've been teaching. Like I have complete silence. And most of the students under 40 are going like, stop that, that's horrible. So what we are gonna do is everybody is gonna do this. You have to do this on your own, but I want you to email me your top frequency and we will make a spreadsheet that I will then mail out to everybody. Or I'll put on Canvas, I should say. So it's really disappointing sometimes, especially as you get older and realize like, oh my God. I did, my mom's got really bad, like she's in her 80s. I did one of these things for her. She couldn't hear things over like a couple of thousand hertz. You know, luckily most vocal stuff is below like 4,000 hertz or something. So you can lose a lot of your high frequency. It's gonna mean your hearing is not as good. You're not gonna hear as much crispness and sizzle and stuff and things. But you know, you have to lose quite a bit before you really lose the ability to make out any kind of words or stuff. In fact, there are both the youngsters and the oldsters have like taken advantage of this, like people who are worried about these young hoodlums loitering outside of their stores will play these high frequency sounds that like a teenager finds excruciating, but anybody over 30 doesn't even hear. The same way that kids in classrooms have come up with like texting ringtones where the teacher doesn't even hear the, you know, phones going off tick, 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 at these high frequencies. So, you know, both sides have kind of tried to take advantage of this for different things. But just kind of putting that out there, you are going to, yeah, I can show here, I can show you, this was 2018. It's pretty clear. You got this nice negative correlation. And you can see the people up here over 40, we're down around 13,000. This included me down here. The young bucks and buckettes are like up 18,000 hertz, 18 kilohertz. So it really, there is a pretty dramatic drop as you get older. So any questions about that part? This part is going to be finding your own personal dot on this graph using one or both of those videos, emailing me that, because I will then make that available for the rest of you. I say here in bold, please email me with your value and your age. I will de-identify this on the spreadsheet, so no one will have to know it's you that is that age. So don't worry about that if that's something you're worried about.
I have children. Do you want some other data points so people can see how dramatically our hearing drops off? They have a experiment like this at the Academy of Sciences, and I did it with my children, and I was really depressed of how much better they can hear than I can.
Yeah, no, so actually that would be great. That would be, because normally I don't have younger kids in the class. So yeah, it is like it is depressing until you realize that you're in the same bucket as the rest of humanity. So and so that is frequency range of hearing. So you're going to be doing sound localization, frequency range of hearing, but not part A, just part B. And again, that's going to be something you just listen. Again, it's going to be, it takes a lot longer for me to talk about than for you to do it. And again, I don't want the age. The age is irrelevant. I mean, I want your age, but I don't want what they say your age of your ears is. I want the frequency. What's the highest frequency that you can hear? So hearing loss. This is the last piece of this hearing lab. I need to give a little bit of background. Whoops, I should have made that second line there. So hearing loss, I've alluded to a little earlier about the job of the middle ear to conduct the vibration to the inner ear. One way to have hearing loss is what's called conductive hearing loss. Because remember, the inner ear, this is where the transduction happens. The cochlea, the hair cells, so the inner ear is where the magic happens to convert vibrations into an electrical signal. But what if the vibration never gets there? So conductive hearing loss is when the vibration is not being conducted into the inner ear. It never gets to the inner ear. What are some of the possible reasons you can have conductive hearing loss?
A cold. Like if you have like an infection in your middle ear or something.
Yeah, so an infection in the middle ear, if it's causing this to, like if there's fluid or stuff keeps it from vibrating well, that could cause conductive hearing loss. There's some kind of infection in your middle ear with, they call otitis media. It means inflammation of your middle ear.
Could there be something wrong with the little, I forget the name, the little bones that are in the middle ear?
Yeah, some, in fact, I know a number of people in my family who have had surgeries to free up the little bones or even to bypass them completely because they have just kind of started ossifying together with the little joints and they don't move anymore. So if they don't jiggle, then they don't transmit the vibration. So you have to either free them up, or sometimes they actually bypass them altogether and directly connect, like the eardrum to the oval window, to try to make it more of a direct connection. So if something wrong with those inner ear, those ossicles, that can cause conductive hearing loss. What's another thing?
A burst eardrum.
Yeah, a burst eardrum. If your eardrum isn't intact or something's wrong with it, then that's that first thing that's, you know, vibrating sympathetically with the air to create the vibration heading in. Even something as, you know, earwax, you know, can cause conductive hearing loss. You know, cerumen. Remember from anatomy, the ceruminous glands making your earwax in your ear. So that's conductive hearing loss. If somebody has conducting hearing loss, one of the ways you can tell that it's conductive hearing loss and not, you know, this is, so that I'd say, let's say this is versus what we call sensory neural hearing loss. This is happening at the level of the actual transduction. Here, the vibration is getting in, but you're not actually creating the signal down the nerve. So how can we distinguish between these two?
When my daughter had a burst eardrum, they put like a little something behind her ear to test her hearing. So like, 'cause I was freaking out that she couldn't hear anything. And
Right.
so they
And
kind
then
of,
she could. All right, so that is one of the tests that we're going to be learning about actually today. That is the Rene test. So here we go. Because all of this stuff is in the bone. Remember, I keep saying this is in your skull bone, temporal bone of your skull. If somebody has conductive hearing loss, you can take a tuning fork, you know, basically a metal vibrating thing, and push it against the skull, which is then going to just vibrate the skull. And because the inner ear is just a little cave in this skull bone, it's going to vibrate the whole inner ear. And assuming you don't have sensory neural loss, it's just conductive hearing loss, you'll hear something. You'll hear this thing as long, you know, you're not hearing it through the air conduction pathways because something's wrong with that. But if you actually put the tuning fork on the skull itself and vibrate the whole skull, somebody with conductive hearing loss will still be able to hear it because it's jiggling the whole inner ear just directly by jiggling your skull bone. You know, what would happen if somebody had sensory neural loss and you did that?
You wouldn't hear anything.
Yeah, it wouldn't make a difference because that's not the problem. The problem is the hair cells can't do their thing. So in fact, both of the tests that we're going to look at involve putting tuning forks on your skull and seeing what do you hear. And I will just show you both of those right now and then show you what you're supposed to do for your lab with them. Let me share screen again. Okay. We can do, so Rene test, this is the one. Oh wait, who was it? Jen? Who just mentioned this one? So one of the ways to check for hearing loss and then to check whether it's sensory neural or conductive is you take this tuning fork and you go bing, you ring it, and then you put it, this is the mastoid process. The mastoid process is a little bump on your temporal bone right behind your ear. It's a good place to vibrate because your inner ear is in the temporal bone. So you're basically vibrating the skull right near where the ear is. So assuming that this person does not have sensory neural deafness, they'll hear something because you're vibrating the skull directly. And you wait until you don't hear anything anymore. And this relies on the fact that our ears are supposed to be using air conduction. They're much more sensitive to air conduction than bone conduction. So you start this thing going, and when you stop hearing something, so this is doom, 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 doom. Okay, I don't hear anything anymore. Immediately, you take it, you let it keep vibrating, and you put it right near the ear canal. And usually if your hearing is normal, you can hear it again because your air conduction is much more sensitive than bone conduction. And typically this should last at least as long as this sound lasted. If you put your timer on and this went for 30 seconds, and then after you stopped hearing it, you moved it over here, you should hear it for another 30 seconds at least before it fades away. What would it mean if I could hear it here, and then as soon as I stopped hearing it here, I put it on front of the ear canal, but I didn't hear anything?
Conductive hearing loss.
That'd be conductive hearing loss, exactly. Because obviously the ear works in terms of transduction. I can hear something, but vibrating the bone is way better than just letting the air vibration come in. So something's wrong with the conduction from down the ear canal to the inner ear. So this is the Rene test. And here you can see why somebody who can't hear because they've got some ear infection messing up their conduction, but they can hear if you put the tuning fork on their mastoid process of their temporal bone, because you're jiggling the inner ear and the hair cells are going woo. So the other test that we do is the Weber test, also known as the unicorn. No, I made that up. It looks like you get to make your subject a two-pronged unicorn. All right, so in this one, you put the tuning fork on the midline of the skull. Sometimes people put it on the front, sometimes people put it just right on top of your head. This one is a little interesting, trying to figure out how to interpret it. So for this to make sense, so you can make an intuition. If I had sensory neural hearing loss, let's say in my right ear, what would I hear? If I had a tuning fork going, bzzz, what would I hear? What would the sound be like in my ear if there was sensory neural hearing loss?
There wouldn't be sound, right?
There wouldn't be sound, or else it would be lower. Let's say, because there's a continuum. So, but I'd have a problem with the sound. So if I put this thing on my midline of my skull and it's vibrating and my right ear is lower, it might mean that my right ear has sensory neural hearing loss. But the conduction hearing loss is a little counterintuitive. Like if you like clog your right ear, like and hum or talk and blah, 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 blah. Which ear is louder when you're like got an ear that's clogged up?
The clock.
Dear,
The clogged ear is a lot louder. I think the sound kind of reverberates in your head and gets more action in there. But so if you have the Weber test and your right ear is lower and your left ear is louder, it might be that you have sensory neural loss on the side where it's lower, or it might be conductive hearing loss on the side where it's louder, on the contralateral side. So what we say is if the sound lateralizes, meaning it moves, if it's the sound is more predominant on one side versus the other, if it lateralizes, it could either be ipsilateral conductive loss or contralateral sensory neural loss, if that makes sense. So, you know, I think, yeah, when you actually plug your ear and talk it, then you realize, oh yeah, it's true. It's louder in the ear that's clogged up, but it's not necessarily intuitive. So make sure you remember that. So
basically that test is not really like a great way to determine like which it is, because it could be either or, is what you're saying?
exactly. So these are always used together. So together they give you more information than either one does on its own. So in fact, that is what we're going to be doing for the actual doing the lab thing. Normally we would do this on each other, but instead, you know, so for part 3, it says here's a couple of videos just describing them so you can like review in case you want to review. And then it says watch the following videos of the Rene test. But it's not just of both. Watch the following videos. I shall edit that. Evaluate the results for patients 1, 2, and 3. Record in your lab book and be sure to interpret. So basically we have this, you know, this woman here who's the patient, this other doc here who is now going to perform the test.
The Rene or Rene test.
We can't see anything.
Oh,
whether the patient has
sorry.
Conductive or sensory neural hearing loss. The Rene or Rene test is used to help determine whether the patient has a conductive or sensory neural hearing loss. The vibrating tuning fork is placed on the mastoid bone behind the ear. The patient is asked to tell you when the sound disappears. At that point, move the tuning fork from the mastoid bone and hold the tines close to the ear canal. If air conduction exceeds bone conduction, the patient will still be able to hear the vibrations in this position. Now I'm going to place this behind your ear. Tell me that you can hear the sounds and then tell me now when they stop. Then I'll move it in front of your ear and say yes when you can hear them and now when they stop again, okay? Yes. No. Yes, okay. Okay, good.
So what do you think about her hearing?
It sounds normal, right? They sound like equal amounts
Yeah.
of time.
Exactly. So she could hear it when it's there. So we knew that she doesn't have sensory neural. And then when she couldn't hear it there anymore and the doc put it in front of her ear, she could hear it again and she could hear it for about an equal time. So that is what you would want to see if somebody's hearing is normal. We have the same person doing the Rene test. I mean, the Weber test, so you can see what that looks like.
The Weber test is used to evaluate for conductive versus sensory neural hearing loss. A vibrating tuning fork is placed firmly on the vertex of the patient's head in the midline. She is then asked to tell you whether the sound is heard equally in both ears or better in one than the other. Normally, the sound is heard equally on both sides. Be careful to hold the tuning fork by its base and do not touch the tines.
Which, yeah, I've had students like not have this work and realize that they just, yeah, they're clamping on the parts that are supposed to be vibrating. So when if you actually do this, remember that you need to leave the fork part free to vibrate, or else it's not good.
Can you hear that equally in both ears or better on one side? I hear it in both. Okay.
All right, so what would you interpret there?
Normal.
Yeah, normal. That's what you expect. You'd expect it to be the same in both. You know, there is another interpretation which could be equal hearing loss in both sides. But in general, you know, this, from looking at these videos, I am not too concerned about this woman's hearing at all. Because, you know, the Rene test looked good, and then we see there's no difference between the two sides here, so the other side's probably good. Yeah, see, it's instead of doing the unicorn thing, she's doing more of like, I don't know, like a Martian thing here. Putting that up on the top of her head. So you're gonna, this is patient one, so you'll record the results for patient one in your lab book and interpret, which we've kind of just gone over together. And then there is patient two and there's patient three. And in both of these, you have a doc and you have a patient, and they're going to be going through both of the tests. You know, and it kind of gives it away, but.
Just hear the noise.
Yeah. Right, so you can see it's the same thing, the same test, but the results aren't necessarily going to be the same. So for patient, this is patient two, you're going to record for his Rene and Weber test and interpret, and then you'll do the same thing for patient three, which is just going to be, it's the same doc, but with another patient. Or actually, yeah. So any questions about what the expectations are for the hearing lab?